Looks like we can start. So, hello everyone. My name is Zehra, and today, first of all, thank you so much, Abhi, for that introduction. Wonderful. Thank you so much. And by the way, you already know about me. So let's jump right into the topic. Today, we're going to talk about the evolution of natural language processing, how we move from having these rule based, very tight, constrained systems to large language models. And so, before we dive deep into the topic, let's hear a story. Imagine this: you travel to a new country, and so there is new language, new culture, new context. And so you open up your mobile phone app, Google Translate, and you write this sentence. Apparently, this is the time where you don't want it to take a lot of time and you don't want it to mess up. So it spits out a bunch of words, and you don't understand because you don't understand the language, and the other person does not understand it either. And now you're thinking, I wish I had learned basics of that language. And if this is so hard for us humans to learn new languages, imagine how hard it would be for machines to understand these languages. And it's not just translating stuff, it's about culture, it's about context, it's also about the meaning that it carries. It's very different from one language to another. So this is exactly what is natural language processing. Natural language processing is that field of artificial intelligence that focuses on enabling computer to understand, to generate, and to interact with us using human language and among each other as well. This is just like how we talk to each other, and we also want that ability to come into computers as well. We can just say something and they understand us. And that is exactly what is NLP. So, what are some of the applications? Some applications include like search engine, you just go up on Google and type something, that is NLP. Machine translation, we just talked about it, translating from one language to another, that is NLP. Voice assistant, you talk something into an app, it translates or it gives out a voice output or maybe a text output, same thing. Voice assistants are also NLP based. Text summarization, sentiment analysis, where you basically want to capture the context of the sentence, what is the emotion behind sentence, that is sentiment analysis. Question answering, all of those are examples of natural language processing. So we wanted the machines to have this kind of ability where they could understand us. So we came up with a couple of techniques. And this is what starts the rule-based natural language processing. So the first technique is tokenization, where we basically have a phrase like a natural language processing. And what you do in tokenization, you just break that down into a couple of words, basically a list of words. So natural language processing becomes natural, another word, language, second word, and processing, a third word. There's another technique called stemming and lemmatization, where basically you change the word and you reduce it to its stem. So the reason why there are two stems, CHANG, Chang, and change, is because one of the technique uses stemming and the other technique uses lemmatization. Now, as you can see, there isn't any word like Chang. So clearly lemmatization is better. And this is why in the real world, we still prefer lemmatization over the technique of stemming. Both do the same job. It's just that lemmatization is much more better than stemming. Then we also have another technique. It's called POS tagging, which is like part of speech tagging. You take a sentence and you tag each word as the part of a speech. For example, I is a pronoun, like is a verb, playing is a verb gerund, and then Sudoku is a noun. So what happens at the back end is that now machines are making certain rules. They are like, okay, we can use tokenization, stemming, and POS taggings to make rules. And one of these rules, this is like a very basic example of one of the rules that machine makes at the back end. So basically they take a sentence, they say, oh, there is a pronoun, there is a verb, like, and there's a verb gerund, so that there is some kind of activity, and there's also a noun. That means this user likes this activity. And this is how the machines are making all the sense at the back end, making these rules so that they can understand what we are saying. Now, moving on, imagine this situation. So that was a single rule. Now imagine this situation. I have different variation of sentences. It's I like playing Sudoku. I really like playing Sudoku when I have time. I don't like playing Sudoku. Sudoku is something I enjoy. These sentences are quite similar to each other. Can you guys tell me how many rules do we need for this? Because that was like a single rule for a single sentence. How many rules do we need for this? I want everyone to, like put that in the chat. How many rules do we need for this kind of system? And so that I know everyone is hearing as well. So do you think we need 10 rules? Or do we need 10,000 rules? Do we need 1 lakh rules or 100,000? So I guess I'll answer that. So we don't know. And sometimes these rule-based systems make mistakes. And when they do make mistakes, we don't know how to fix them because we don't have generalization. We don't have like, hey, you did this wrong. You can fix this by using this kind of loop. And we don't have a feedback loop. We cannot tell it that you did an error in here, so you need to fix that. And so there is no improvement. And in order to make sense out of language and in order to form on the basis of history of language, just like I told you, there were so many sentences which are similar to each other. How do we make sense out of it? We need lots and lots of data. And that's where statistics or statistical NLP come into the picture. So there are many statistical NLP models out there, but I've included very few of those. There's one called the N-gram model, which basically uses previous N number of words to suggest what the next word will be. And then there's hidden Markov model as well, where it's basically like if it's rainy today, what's the chances of being rainy tomorrow? As you can see, it is 70% because the rain turns back to rain with a 70% chance. And rain goes to sunny. So it goes from rainy to sunny with a 30% chance. And if you don't have to, if the maths is not making, if the maths is not mathing, it's all right. It will all make sense. And then there's also another one called naive based classifier where we take the entire previous data. So we have the data from past where we check that the word amazing in positive reviews came 50 times. You can look at the table in this picture as well. Like the word amazing came in positive reviews 50 times. And the word amazing in negative review came only 2 times. So they also had a couple of sentences and they also figured out that if there were 10 sentences, the probability or the chances of it being positive was 60%. So using all those probability, they decide whether a certain sentence can have a positive emotion or it has a negative emotion. For example, here's this sentence called amazing food but terrible service. Is that positive? Is that negative? I mean, it's quite confusing. There is the word amazing, there is the word terrible. I mean, you can make sense out of it. It's like a neutral sentence where they're saying that the food is amazing but the service is terrible. But at the same time, it's not so simple for machines to make sense out of it. So they have to use probability at the back end. And so this is how naive based classifier says that for it to be positive, there is 0 point on the very right. You can see there is 0.003. And for the negative, there is 0.0036. So the negative is slightly more, but you can see that they are very close to each other. And so it's not as simple as it's look. And even with the statistical NLP, we still haven't figured out the problem of feedback loop. Like we are not making improvements. Yes, there is a whole bunch of data. We make some rules. We say that, oh, amazing appeared 50 times. But what happened if we want to apply this on coming data? And our data is also changing. We don't change the data at the back end. We are using the same 50 reviews that we have in the previous days. So how do we improve these systems? We use deep learning. And by deep learning, we are updating something called as weights, which is basically like updating certain mathematical variables in the system so that we can update how our model fits to the coming new data. So that is why we came up with deep learning. And so just like we talked about this, amazing food but terrible service, is that a positive? Is that a negative sentence? Just like here, I like playing Sudoku is positive emotion. How can we solve that using deep learning? Now, based on our previous data, we can feed that into a recurrent neural network. And there are two kinds of those recurrent neural network. So what is neural network? Recurrent neural network is basically like an example, or it's like a type of deep learning model for language based scenarios. So in this situation, you can just take this sentence, I like playing Sudoku. You can put that into an LSTM. You can train that model based on your previous data, and it takes out a single number that tells you whether this is a positive emotion or this is a negative emotion. So you are basically classifying one sentence and two emotions for that. There can be multiple emotions as well. So you figure out, oh, this is a positive or negative. But my question is, what happens if there is a sentence and you also want to output a sentence? Because this right here is just putting out a single number. But when we talk, anything that I say in English can get translated and have many more words. For example, look at this example. I like playing Sudoku in English is 4 words, but I convert that into Japanese, it is 8 words. But the previous system is only putting out a single number. So that also means that the single LSTM that we just talked about, or you could say the single deep learning recurrent neural network, doesn't solve the problem of variable length. It doesn't solve the problem when you have a language where there are number of inputs and you don't want to put out a single value, but you want to output multiple values. It just doesn't solve that problem. And so we came up with a solution that, hey, instead of using a single LSTM or a single recurrent neural network, we can use two recurrent neural networks. We can use two LSTM where one is doing the job of converting it into some kind of representation or the vector, and that can be an input for another LSTM that translate that into a completely different language. So you are solving this problem. You are putting in 4 words in English and you are taking out 8 words in Japanese using two LSTM joined together. And this is how we came from having a fixed output to having multiple or variable length output. And this is exactly what is sequence to sequence, where you convert a sequence to a sequence. The reason why it's called a sequence is because language is in sequence and it carries meaning in sequence. One word has a meaning dependent on previous word, and it also will influence the words coming after that. So that is what we have solved. But you might assume that, hey, the problem is solved. So, I mean, I can go home and make my own translation system with these LSTM. But here's a catch. Look at this sentence. I mean, it's pretty long. If I tell you to read it once, just read it once. Can you just read it once and can you think about it and can you just translate this easily? I mean, looking at the previous architecture, we are saying that one model takes in all the English sentences, it converts and compresses that into a single vector or a number, and then that number will be a representation for a completely different language. So imagine this, like these many sentences are so much for a single encoder or a single LSTM. This is so much pressure. This is pressure for human brains. Imagine how much pressure it would be for a machine learning model. I mean, it's maths at the back end. And so this kind of system is putting too much pressure on one recurrent neural network or on one deep learning model. So what's the solution for this? I mean, it's hard because these are like so many sentences, you are losing context, you are losing meaning, and you have to translate these so many sentences at once to another language. Too much pressure. So imagine this, when you're reading a book, you try to focus on certain words. And if English is not your first language and you have a hard time speaking English, or maybe if you're a new speaker in English, then you know this, that you read a word and you try to translate that into your brain. And you read another word and then you try to translate into your brain. This is how human brains work. And I mean, it would be so much better if machines could work like this. Instead of taking out the entire paragraph, they could just focus on a couple of words. For example, many of the trees, I can just think about it in my language, which is Urdu, and I can say, bahut sare darakht. And this is what we needed in machines. This is what we needed in the previous system of translation. Rather than taking out so many sentences, putting that out, just giving it a one chance, like, hey, this is just one vector, use it to translate in another language, putting in too much pressure. Machines rather focus on certain word at a time. So it can be like, oh, many of the words can be translated to this, and which had lost their leaves can be translated to this. And this is how the newer machines are working. This is how the backends of many large language models are working nowadays. So rather than saying on the left, you can see this is like the previous model that we were using, where it was putting out a single vector, single number, and then it was getting translated. Rather than putting out a single vector, that vector gets updated. And this is how what we do it in deep learning models. We update those vectors, we update those values. And rather than having that single vector, we are updating it from time to time. So like many of the trees has a different context vector. And as you move on to another words in the sequence, the context vector gets updated every single time. And so this makes it much more easier for machines to understand that we can focus on a certain word, translate that, come back, focus on another word, translate that, come back. And this is exactly how machines are coming very much nearer to how a human brain works. And the reason why I'm telling you all of this is because attention mechanism is something which sits at the back end of transformers. And transformers are nowadays the backbone of large language models. But hey, wait. It's not just attention mechanism that sits at the back end of transformers. There are many more other techniques like feed forward. There is a softmax layer. A whole deep learning architecture sits at the back end. But I'm saying that attention mechanism is something that has revolutionized the entire process on how machines do language tasks. And this is why transformers are so much more important to understand in today's world. This is like one of the hottest topic in NLP right now, where people are trying to improve these language models. And so with large language models, I mean, yes, this was all the talk about it. So far, if you have any questions, I would like to answer those. I mean, we can always go back and talk about a little more on certain architecture if you want. If anyone has any questions. Okay, so what you can do is that if you want to understand these systems a bit more, in depth, for example, if there were some things which were very confusing because these have a lot of maths at the back end, you can always go to Campus X, which is a YouTube channel. And this guy is basically explaining you all of these systems. And a lot of inspiration for this workshop came from his videos as well. Now, unfortunately, I cannot explain that much math without having a whiteboard on screen. I would love to do that, but because of the time constraint, it's rather impossible. And you also need to have some kind of prerequisite in terms of deep learning models. My goal for today was to convey that in the form of story so that you can go back and you can say, natural languages seem like a great interest topic in research. Like it's a great topic in research, and you can go back and read about it. And maybe you can start building on your own systems, or you can start doing some kind of research at your university or your even at high school level, if any of y'all from high school. So if you go to Campus X, it will make it much more easier for you to understand and read some of these research paper which have changed the whole realm of large language models. One of these is like the sequence to sequence that we just talked about, how there was a single LSTM and it was converting it into a single number. So we rather decided to use two models rather than having a single one. And that's what we talked about And that is exactly what is in this research paper of sequence to sequence. You can also read about attention is all you need. And anyone who is coming into NLP, natural language processing, I think they should definitely understand and read about attention is all you need. What you can build with this kind of knowledge, or what you can do next, like you don't, if you don't want to read papers, it's fine. I mean, they are quite convoluted, I do understand that. But what can you build with this? So you can build a retrieval augmented generation. It's very simple. You can take a bunch of paragraphs and you can put those into, you can basically program, and you can use these frameworks like LangChain, LangGraph, and you can make a model where you put in a bunch of PDFs and you can chat with those PDFs. For example, you have many like PDFs that have questions and you want to prepare for exam. You can build a rack for that, and you can just ask it a certain question like, hey, what is a certain X or certain Y, or how can I solve this? And this RAG system will answer it for you because it uses LLM as well as all the PDFs which are from your syllabus. So we are basically combining the intelligence of large language models with your domain knowledge or with your PDFs, and it makes it so much easier for you to now understand all of these PDFs. You can even make your own transformers. You can even make these transformers to get input of images. I mean, images, languages, all of these are just numbers for computer. So a transformer that can be built for a language can also be built for images as well. And you can even use these large language models to build your own agents. That's exactly what I am doing at my current workplace. We are building agents using these large language models. And I think that you can just do so much more with NLP, and you can combine NLP with other deep learning applications as well. Like with the vision transformer is basically like a combination of two types of deep learning tasks. And so if you have any questions regarding these systems or regarding these papers or even anything related to NLP, you can reach out to me on LinkedIn and you can check out my projects as well. So what I do is that I wanted to learn NLP and it was quite convoluted for me. So I had this idea that I have a couple of medical reports and I often forget what is my blood type or what was my last reading for this blood level or sugar level. I forget those. So I made a retrieval augmented generation for that. I just put in my reports. I write that, hey, what is my blood type? And the machine answers it for me. I don't have to look through so many reports every single time I sit down. And you can make those systems. And I put that, one of these systems we put in using the large language model, it ended up becoming one of the systems being recognized at regional level in here in Pakistan. So you can do so much more with these systems. And if you have any question regarding this system or even this entire realm of natural language processing, I would love to answer those as well. And if this was too convoluted, I'm really sorry because I didn't know that what would be the level of incoming audience for this workshop. So I decided to convey this with as much storytelling as I could. So yeah, that's it from my side. Thank you so much for inviting me. If you have any question, please ask away.
Thank you so much for that quick session, Zehra. Honestly, as someone who's South Asian myself, it's always amazing seeing people do so much in especially STEM related fields. That was the whole point of why we made STEM Quest in the first place. We wanted to get people to explore different fields within STEM. So with that being said, if you guys have any questions, any comments, please leave them in the chat and Zehra will get to them. And once that is done, we can conclude the session.
Thank you so much, Mariam. That's so kind of you for saying that. Abir, I would also like to share one thing with your audience. There is this system that we built where we wanted, so you see with educational platforms, we have a bunch of questions, we answer those. And the system doesn't give us feedback. Like, it doesn't tell us what we are doing wrong. It doesn't tell us that, hey, you were weak on this topic, or you were weak on this certain topic. And we made this system where we were using large language model, and we were giving automated feedback to students. So based off, like, they were wrong about a certain question. For example, they didn't know about deep learning or neural network, and they did that particular blank wrong. So our system would tell them, by taking out resources from the internet, that, hey, these are some resources, you can go and read those. And it will strengthen your base for understanding deep learning. And you can build these systems yourself, like literally at home. Like, there's this platform called Grok Cloud, not the Grok X, Grok Cloud. And you can go there, you can create your API key, and you can use their large language models to create these systems. And I would like literally, like, if I knew this a bit earlier, I mean, I would be building these systems in university. So if you're in university, or if you're a high school student, please go to these hackathons and build these kind of systems. I truly mean this. Like, you cannot do so much at home on your own that you can do in these hackathons and in these competition. And you can build so much more in these systems, because you are pressurized and then you have to work so much. So yeah, go to hackathons, explore competitions as well. And I mean, it can be good for you and your future as well, to build skills. Yeah, that was it from my side. Yeah, I can put those names. Just give me a second. So this is one resource which you can use for creating API keys. API, I'm writing that as well. So you can create an API key from here, and you can use that into your website. And you can literally basically have a large language model child in your website. Like, that's like the easiest way to explain this. And I'll share one more resource with you. This is very, like, it's very interesting. Just give me a second. I am looking up for dev post. Okay. So this is dev post, and this is for hackathons. So the hackathons on the dev post are a bit easier. They are longer, like sometimes they are 10 days. So if you're like too new to the field, and 2 days or 3 days are too less of a time for you to build systems, you can go to dev post. They have very long hackathons, and I mean, you can build a pretty good system in this. Now, this is a bit harder. Lab AI is mostly like 2 days or 3 days of hackathon. So it's a lot more pressure to create systems during lab AI. And the system that I was talking about, I would also like to share that as well. And this will be the last resource. Sorry for too much talking. This is a system that we designed, and this was recognized at a regional level in Pakistan. I mean, it didn't win the regional level, but it went to the regional level. So yeah, that's one of our projects. Very interesting one. Go check it out. There's a video as well, so you can put on the video and understand how the system is working. So yeah, that's it from my side. Thank you so much, Abhi, for inviting me, and STEMQuest as well.
Of course, thank you so much, Zehra, for your time and the time you took out from your very busy schedule to be here. I'm pretty sure everyone really appreciates it. Thank you so much. And with that, we can conclude the session.
Bye, guys.